On to titrations. So, um, yeah, just I like this figure, but wish it had a burette. I spent some time trying to get AI to do it, but gave up. So on the simulation on my website, you're going to find just mostly focused on one type of problem, but so we're just mixing weak acid or strong acid, and then trying to determine what's the pH afterwards. All right. And so the end result is we have really two main types of problems here: strong acid, strong base titration, or a weak acid, strong base titration. And I think it's nice to kind of visualize where you are. So like 66% of the solving is going to be the same and a lot of steps on these problems, but in the end, the finish is what's going to be mostly different for them. And so, if we look at it, the initial pH for a strong acid, then the very starting, since it dissociates completely. So if we look here and we're not given a Ka versus in the weak acids, we always give you the Ka for it. Say the Ka, say the Ka is this. Here we don't. And so you should be able to recognize the strong acids, but if not, that's your clue for it. And so then essentially that concentration, this completely dissociates, and that gives you the concentration of your strong acid. The difference is when we're at a weak acid over here, now we have to use Ka. And so you use K, there's no base added here, that's before any. And so you just simply have Ka equals X squared over the starting concentration of the acid. And here X is going to equal the H plus concentration, and then you can go find the pH. Afterwards, after we start adding, then we have two things happening. We have the dilution because we're increasing the volume, and we have the neutralization because we're adding base with it. And so that's what makes these problems so difficult. Okay, so what are the steps? So all titrations, then we have the stoichiometry component. And because we have the difference in the volumes, then we have to take it to moles, or I recommend millimoles. And because the volumes are often in milliliters. So you can do that if you're comfortable, but you can certainly keep it in moles. So you got to find the moles of the acid, moles of the base, find the moles of the remaining. So that's the stoichiometry part. And for a strong acid, strong base, you have to take those moles back to concentration, and then you can find the pH if the acid's in excess, or if the OH is in excess, you find POH, and then you simply convert POH to pH by 14 minus POH. If you're using a weak acid though, and you get to the moles of the remaining species, then you can actually stop at the Henderson-Hasselbalch. You can plug in moles here or molarity with it. All right. And so at the equivalence point, then you have to do this one little step here. All right. And I'll talk about that more in a minute. So in a strong acid, strong base titration, then we look at these kind of problems. And here we didn't add any, so I'm just going to focus on this first one. So you can calculate the moles doing just stepwise like this. I like to do like an ice table for it. And we can see you have to expand it a little bit. So normal ice, we have initial change in equilibrium concentration. But the problem is we have to get it to moles, right? And then take it back to concentration. So we have the volume concentrations of the species, and that'll allow you to solve for the moles of these, and then you'll be able to do your normal kind of stoichiometry with it. So let's focus on this problem and see what it looks like. So we have a volume and a concentration for the acid. So that allows us to calculate the moles of the acid. And we have a volume and concentration of the base. So that allows us to calculate the moles of the base. All right, and now that we have those moles, we can do our stoichiometry. And so this is the limiting reagent, so it's going to go to 0, so that dictates what that X will be. And so we get the same thing. And one kind of thing is, I think in the simulation, then it's always monoprotic, monobasic, or something like that. You may have diprotic, and so you can set up the stoichiometry with HCl, or what I recommend is take that, like if we had H2SO4 versus HCl, if you write out the equation for H2SO4, then you'll get the moles the concentration of the H doubled, and then it'll work out the same as this. Okay, so we're getting the moles of the H left over, the moles of the hydroxide is easy, it's 0. And now that we have the moles, when we're at strong acid, strong base, we have to get it back to concentration. So that way we'll have the concentration at H plus, and we can find just like the pH, just like the initial, where we just have that concentration of it. And so here you'd simply take the moles that you have and divide by the total volume, and that gets you back to concentration. So if you keep it millimoles, so millimoles over milliliters, the millis cancel and gives you moles over liters, molarity. And now that we have this, we can simply plug it into uh, uh, to minus the log of that concentration to get the pH. If the base was in excess and we were on the other point, which I'll remind you down here, that would have given us POH. And so then you would have to do 14 minus to get that back to pH. All right, so hopefully now you feel comfortable with all the steps of a titration for a strong acid, strong base. So the initial we looked at here, we're mixing some and the acid was in excess, but you equally could find where the base was in excess up here, and that would then give you POH because that's the species and minus log of it's giving you that. Here, this is for me just a conceptual problem. So if you have a strong acid, strong base, that pH is going to be 7. If we have a weak acid with a strong base, it'll be greater. And if we have the opposite, weak base with a strong acid, it would be less than 7. So that's what I want you to know from it. All right, so now let's look at doing the same thing with a weak acid. All right, so again, we're given a Ka. And hopefully you recognize this is not a strong acid, so that's why you know it's that. So the same stoichiometry is the same for all titrations. So we simply plug in the numbers and we can find the initial moles or millimoles. And now that we have this, we can do our stoichiometry. Again, the base is the limiting reagent, so that's going to go to 0. In a weak acid, though, we have to keep track of the conjugate base. And it always follows how much hydroxide, right? Because that's what's happening is the acid, and again, I wrote this as HA because it's not all deprotonated. It's not a strong acid, all right? So at the equivalence point, it will be, but before that, you still do have HA as your proton source. So, and you'll see in a second. So it always follows. In the beginning, we have just HA, we add base, the base deprotonates the HA and forms some A minus. So this just follows exactly. So now that we have this, then we can find the equilibrium moles of it, and we can stop there. We don't have to take it to concentration, but it's okay if you do, just like the other one. Then we can simply take those moles and divide by total volume, get molarity, and just get comfortable with it. But I'll show you, you get the same number if you do it both ways. So now that we have this, we can find the pH using the Henderson-Hasselbalch. We take that Ka that's given and take the minus log of it and get the pH, just like minus log of H plus gives us pH, minus log of Ka gives us pKa. That's the similarity. So we can simply find those concentrations, plug it into this, and you should get this number with those millimoles. And here I'll show you, you get the exact same answer if you use the concentrations. And why it works is because over here we have millimoles over millimoles. And how would we get that to molarity? Is we divide both the top and the bottom by the total volume. And so since you're dividing the top and the bottom by the same thing, it's effectively 1. All right, so that allows you then to solve for here. The initial pH would be the same if we just had Ka. And so K, you could use that cheat code, Ka equals x squared over the starting concentration. And that'll get, when you solve for x, that gives you your concentration of your H plus. And you can go directly to pH just like with the strong acid. But after we add some base, now we have to use Henderson-Hasselbalch to solve that. At the equivalence point, though, this is different. Now it's not going to be the pH 7, it's going to be greater. And so for that, what we have to do then is you're going to then just look at this conjugate base and look at reprotonating it. So that plus water forms some hydroxide. So what we have to do is convert the Ka to Kb using Kw. And then you can use your cheat code again. So Kb equals x squared over the starting concentration. So you do need this to be converted to concentration. Um, and when you solve for x for that, that x is going to give you the OH concentration. All right. And so then you'll then do 14 minus that, and you can find the pH at the equivalence point. I won't ask you to do one like this in my class. It's a lot of steps, but you will have just given the salt at a certain concentration and be able to solve for it. And then it's just that last conversion part. All right, so that's it. Hope that helps.